Hi everyone, this is Salman Khalik, and this is the continuation of the video series I started, Machine Learning from Scratch. In the last video, we discussed the intuition behind simple linear regression, and we talked about at the end that in this video, we will be deriving this equation for which is technically the slope of the straight line, and this equation which is the y-intercept of the straight line. So we will be deriving these two equations. Right now I haven't discussed what these crazy looking things means. What is this yi minus what is this y bar or y hat or things like that. So I'm going to break down everything as if you are just a beginner in mathematics. So simple basic algebra, we are going to get started from there. Now, if you don't know the intuition behind what these m and b values are and what do they do or how do they affect the linear regression, I would recommend you watch the previous video, the intuition behind simple linear regression. I will leave the link for that in the description below. Now let's get started to derive these formulas. So by the end of this video, we will know where exactly we are getting this formula and this formula from. So we will start with a simple basic example, and we are going to use that example to understand how we are getting m equals something like this and b equals something like this. So let's say we have an example. So I collected data for about 5 students in my class, and I asked them how many hours of study they did, and I know what marks they got out of 100 in their exam. So I just collected the data of 5 students. In real life scenario, 5 data points is not enough. But since we are doing everything from scratch by hand, not using any computers, for now in this video, I will stick with just these 5 examples because we would be calculating errors for all these 5 points again and again and again. So it's convenient this way to use less number of points. So the first data point is telling you that this student studied for 4 hours and got 40 points. This student studied for 6 hours and got 50 points. This student studied for 5 hours and got 60 points. This student studied for 10 hours and got 85 points. And this student studied for 8 hours and got 80 points. Now, I want to visualize what kind of a trend one column has as compared to the other. I want to determine, is there any relationship between these two quantities or not? So just by looking at numbers, sometimes it does not give you an idea. Even though these are very few values, you can see a trend: less number of hours, less points, less marks, more number of hours, more points. So what I want to do is I want to visualize it. If I have thousands of data points, I won't be able to do it just by looking at it. So visualization usually gives you a good idea. That way you can figure out, yes, there is a trend, and that trend, whether it is a linear trend or not. If it is a linear trend, then we can use simple linear regression. So I will make sure that this does look like a linear trend. So let's plot this on a particular graph. Let's make a graph very quickly. So for example, I have x-axis and I have y-axis. So this is our y-axis. Now, first I need to determine which variable should be my dependent variable and which variable should be my independent variable. For that purpose, you can think of that this is hours of study, which means time does not depend on anything. Time does not stop for anyone. So time here should be the independent quantity, whereas marks are dependent on how much time you put in preparation for the exam. So this should be your dependent quantity. In our last video, I talked about that independent quantity is what we put on the x-axis and dependent quantities is what we put them on the y-axis. So which means my y-axis would be the dependent variable. That means I'm going to put how many marks a student got on the y-axis. And on the x-axis, I will put hours of study. So let's graph it. So first of all, I need to take a scale here. On the x-axis, my lowest number is 4, the biggest number is 10. So maybe I can do is, I can say 2 boxes is 2 hours. So then this would be 4 hours, this would be 6 hours, this would be 8 hours, and this would be 10 hours. And it keeps on going, but since we don't have bigger values than that, I will just keep it there. On the y-axis, I can see I'm going in the range from 40 till 85. So I will say maybe, so every 2 box is 20 marks. So this is 20, this is 40, this is 60, this is 80, and over here is 100. The first point would be somewhere here. 4, when the student studied for 4 hours, got 40 points. So my data point would be somewhere here. When the student studied for 6 hours, got 50 points. So 6 hours got 50 points. It would be somewhere over here. Then when the student studied for 5 hours, got 60 points. So 5 hours would be somewhere here. And then the student got 60 points. When the student studied for 10 hours, got 85. So 10 hours and 85 would be, maybe I would say somewhere in the middle of this. So this is 10 and this is 85, somewhere here. So I'm going to do here. And when the student studied for 8 hours, got 80 points. So 8 hours got 80 points. Now, this is the data right now I have. Do you see any trend in this particular data set right now? So if you see a trend, then that is what we are looking for. Whether the trend can be defined by a straight line or not, that is what linear regression does. And I need to figure out the best fit line that can define the trend. Now, how do I know which line would be the best line? So let's say I will think of a straight line first of all. So I will make a random guess. So maybe I will take a guess over here. So let's take this value. So let's say this is the line which is representing the data points. Would this be a good fit line? So let me, or maybe I say that the best fit line would look something like this. Now, which is a better line? Just by visually doing it, we can see that this line, or I would just change the color maybe, so that we can differentiate it easily based on the color. So maybe I will say this line is a best fit. Whether blue line would be a best fit or red line would be a best fit, visually we have eyes, machines do not have eyes. Machines only understand numbers, which means over here, there should be a way to calculate a number, which machine should be able to do that. And then machine can compare which line is giving me a small number. And we would call that number the loss function or the error of the best fit line. So what kind of an error I can think of over here? Now, so I'm going to solve based on the blue lines. What I can do is so let's say if this line is the line which is summarizing a model for us or figuring out the best fit line. So whether it is a best fit line, how do I do that? I can see this is the value this model is predicting. So let me change the color here. So this is the value the line is predicting, and this is the original value. I can find the distance or the difference between these two values. Similarly, this point is this far away, so I can find this distance. This is the predicted value, this is the original value. Similarly, on this point, this is the predicted value, and this is the original value. What I mean to say is, originally in the data, it is given that when the number of hours studied was 6, the student got 50 points. But my line is telling me that if the student studied for 6 hours, that student should be getting somewhere around 65 points. So there is an error here, and I can find that error. And similarly, over here, my predicted value is somewhere 65, but my original value is 85. So there is an error here. Similarly, over here, my predicted value is 65 again, but there is an error here. One way to do it is add all these differences. So how far my prediction is for each point. If I add those differences or those distances, I would get a total error. Now, first, before I do that, what exactly this distance, the predicted value minus the original value, or you can say original value, y original minus the y predicted. What I'm doing is I'm finding this distance for every point. And then once I find it, I will add it, which means this sign that I just introduced is what we call the summation sign. Summation means I'm adding this bracket for every data point. The first value, I will put the original value 40 and the predicted value 65. So for the first value, I would get the answer. Original value for the first point was for 40, this one, minus the predicted value, which is 65. Then I will add 40. So what is the original value? Original value for the second point, for when it was 5, it was 60. So original value is 60 minus the predicted value, which is 65. How do I know this is 65? So this value is 65. So this horizontal line is telling me that this line is predicting 65 for everyone. Then for the third point, the original value is somewhere here, which is 50. When x is 6, y is 50. So that means this is the original value. I subtract the predicted value from it. Then I keep on doing that for the next 2 points. For this point, my original value is 80 minus the predicted value is 65. And for the last point, original value is 85 and the predicted value is 65. When I add all these numbers, I will get a number here. Let's add them. So 40 minus 65, if I do that, I will get negative 25 plus 60 minus 65, I will get negative 5 plus 50 minus 65, I will get negative 15, which means all the values which are below my predicted line, I'm getting a negative answer for that. And all the numbers, these two numbers which are above, you can see 80 minus 65 is going to give you what? 15 plus 15. And 85 minus 65 is going to give you 20. Now let's add them up. If I add them up, all these numbers, so negative 25, negative 5 is negative 30, negative 30 and negative 15 is negative 45, negative 45 plus 15 is negative 30, and negative 30 plus 20 would end up giving you negative 10. That means the overall error is negative 10. Now, this is what I got when this blue line I assumed was my predicted line. But remember, we made a red line which was looking a better fit. For example, if I make a line over here, this line I can see it fits comparatively better. The distance, this distance is smaller as compared to all the other distances. If I find that, that is what I should be aiming for. Okay, so that is what I should be aiming for, but I would do that later. But right now I need to talk about one thing. If you look closely over here, you can see this y original minus y predicted. So I'm going to write this term as y originally minus, I'm going to write this term as y hat. So this is my y predicted value. So I'm calling this y only and I'm calling this y hat. So this kind of a thing, we call it in simple calculus, we call it a hat. So this is y minus y hat. This is the original y minus the predicted y. If you want to keep on writing like this, you can do that, but you can see I have to write more. So that is why these notations are really helpful in mathematics, so that you need to write less. But you can explain more by writing less. Now you can see that here I did over here is something like this: y1 minus the predicted value. That was the first bracket. Then I added y2 minus the predicted value. Then I did is y3 minus the predicted value. Then I did y4 minus the predicted value. And finally I did is y5 minus the predicted value. Now, these are just 5 points. What if I had 1,000 points? I would write all these brackets 1,000 times. That's a waste of time, right? And this is where this summation sign comes into play. I can say that I can write an I here. So if you have done some programming, you have done for loops like for I in range, something like this, something to something. What it does is basically I is just a number. Maybe I'm going from 0 to 10. So first I value would be 0. Then when the loop runs, then the next time loop runs, I value would be 1, 2, 3, 4, 5, and so on. So this is technically, if I write I, that means I can use it or I can show it in this notation. This is telling me that I have to add this bracket, and what I need to change is this I, and this I value ranges from 1 to the value n. Here we had only 5 numbers, y1, y2, y3, y4, y5. So here I can write 5 for now. But since we are deriving an equation, a general equation, so I would not stick with just 5 number, I would stick with n numbers. What if I have n amount of data points? So this I equals 1 is telling you that my range, this I value ranges from 1 till the value n. And these I values are integers. That's why I'm using the word I. Okay, so I don't know whether there is another reason for that or not, but this is what I assume. Now this is an easier way to write. So what this is called, this is the sum of all of these brackets. What of these brackets? So this bracket is the residual of 0.1. This is the residual of 0.2. This is the residual of 0.3. This is the residual of 0.4. This is the residual of 0.5. If I add all of them up, I should be getting sum of residuals, which means I can maybe use sum of residuals over here. Let me show you why this error is not a good error metric. Because let's assume I have another data point. A student studied for 11 hours and that student got 75 points. Let's plot it here. So this is 11 and this is 75 somewhere here. Which means if I figure out this error, I would get what error? I would get 75 minus 65. And that would be plus 10. And if I do plus 10 here, you can see my residual error would end up getting what? My residual error would end up getting 0. But let's make a best fit line. So because I can see this line is not a best fit, I can get a more better fit with this line. Because this line, it seems like the distance from every point to the line is comparatively less for this line as compared to the other one. But how come this line is telling me the error is 0? What is happening? I need to ignore these signs. So the ones which are below the line, I'm getting negative answer for that. The one which are above the line, I'm getting a positive answer for that. And positive and negative are canceling each other out and giving us the impression that our error is low. That does not mean it is the best fit line. So what I need to do is I need to ignore the signs. I just need to add the absolute error, which means this sum of residuals is not a good measure. What I need to do is I need to take absolute error. That means I need to do exactly the same thing yi, original y minus the predicted one, and whatever answer I get, I need to take an absolute of it. What is an absolute function, first of all? So anyone who is a beginner, I would break it down for you. So absolute function is a function which never gives you a negative answer, which means it will make anything that is negative to positive. So when you put anything in these bars, whether it is a negative number, it will end up giving you +1. If it is negative 20, it will give you +20. If you put a positive number, you will still get a positive number, but if you get a negative number, you will get a negative number. Positive number, which means absolute function has the ability to ignore the sign, negative sign, and look only at the numbers, not at the signs. So absolute function, you can understand in simple way that it always and always ignores the signs and look at the magnitude only, or the numbers only in simple terms, which means over here, I can replace this bracket. I can replace this bracket. Maybe I will just highlight it. I can replace this bracket with these bars. So when I say I replaced it with this bracket with these bars, what I ended up doing is I simply ignored all the signs, which means if I go back up and I ignore this sign, this sign, this sign, and add all of them up, now my error is pretty big, which means if I do this over here, my error is going to turn out something like this. When I goes from 1 till the value n, for all this, first of all, what exactly I'm going to call it? It would be sum of absolute errors. And I can give them labels. For example, the short form for sum of residuals, or simply sum of residual errors. For this one, it would be sum of absolute errors. Now, if I calculate the sum of absolute error over here, I would end up getting. So let's go up here and let's get these values. If I'm getting sum of absolute errors, I should be getting what? 25 plus 5 plus 15 plus 15 plus 20 plus 10. And if I add all of them up, this would be 30, plus 15 is 45, plus 15 is 60, plus 5 is 65, 65 plus 25 is 90. So we end up getting equals 90. And you can see it is way poorer than what we were getting here. And that was close to 0. If I want to, yes, I did add this 10, which means you can see my error is pretty big now. If I ignore the sign, this tells me my points from the original line to the predicted line are so far away. 90 total, the distance is 90. I want to reduce this 90 to 0. I can make it 0 by doing this if I just do sum of residual errors, because many lines can do that. You can figure out so many lines. This horizontal line was doing it, and this horizontal line is technically telling us that no matter what you studied, the examiner is giving everyone 65 points. That is what is happening over here. Do you see the point here? What is happening over here is whatever examiner is doing, how many hours you studied. You studied 11 hours and you should be expecting a fair points, right? Means the examiner should be grading it. It is as if like examiner thought of it, I'm going to give everyone 65 and ignore whatever they did in the exam, and that examiner gave 65 to everyone no matter how much they studied for. Somebody who did not study get 65, somebody who studied a lot got 65, and that's not fair, which means this particular idea of this line is not right, and residual errors is not a good measurement. Absolute error would do the job, but there is some sort of issue with the absolute function. If we draw an absolute function, the absolute function looks something like this. So it has a line. So the graph looks something like this. It is like a V. It will always and always give you a V kind of a shape. So this kind of a shape. So this would be the function, absolute function. So if I say absolute of x, this is the function. You can see no matter what is the x value, whether x value is negative or the x value is positive, the y value is always above it. What is happening at this particular point? At this point, it is not differentiable. When I say not differentiable, now for any folks out there who has not taken calculus, let me put it in simple words for you. Not differentiable means, so I'm assuming you have at least did high school, even if you did not do calculus, introductory calculus, you have done high school algebra or pre-calculus. If you have done that, you know what is slope means. So not differentiable function means at any point that if you zoom into that particular point and look in the neighborhood on the left hand side and the right hand side, and you figure out the slope of the points in the neighborhood of that point. So let's zoom into this particular point. So let's take this particular point. At this point, what is the slope? It is a straight line. The slope is negative here. I don't care about the number. And on this side, when you zoom into this particular point, because this is a V shape, that means the slope is negative, 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 and suddenly at this point, the slope is, I don't know what that is, and suddenly it became positive. Means it's instantaneously got changed from negative to positive without going to zero. So it's kind of like you are driving a car and you are going forward at a particular speed. Without coming to rest, you started moving backward. That does not make sense, right? In this absolute function, this is what is happening. A car is going in reverse. That means it has a negative gradient, negative slope, and suddenly without coming to rest, it started moving forward. That only happens in cartoons, and this is reality, so it doesn't happen over here. So this absolute function does not make sense at this particular point. So which means suddenly this slope changes from negative to positive without coming to zero. That gives, or that makes this function not differentiable at this point, because this is the point where the differentiation goes crazy. Differentiation is not possible. That means slope on left and right hand side are not matching. That's why it is not differentiable. And if it is not differentiable, machines do not like that. And if machines don't like that, we need to hard code a particular value at this particular point. If we don't do that, your machine is going to throw in the errors. We don't want to deal with the errors right now. So can I avoid this? I can avoid that. How? By using another way to make these residual errors positive. I need to think of another way to make the signs of these numbers positive. And the other way is by taking the square of every number. That means if you take the square of this particular value, so which color should I use here? Let's use black. So if I square this value, this value, this value, this value, this value, this value, which means 40 minus 65 will give me negative 25 squared. This would be negative 5 squared. And this would be negative 15 squared. this would be plus 15 squared, and this would be plus 20 squared, and this would be 10 squared. And when I add all these up, I would be getting a big number. I don't care about that. I'm calculating the error. The thing is, I'm just ignoring the sign. I need to ignore the sign. Ignoring the sign is the important thing here. So if I add the error, 25 squared plus 5 squared plus 15 squared plus 15 squared plus 20 squared plus 10 squared. If I add all these numbers, I will get an error about 1600. What I did over here, previously I took the absolute and I called it sum of absolute error. Now I did the square and I added them. So technically what I got is sum of squared errors. So I would call it sum of squared errors. And my equation is going to turn out to be summation from I value 1 till n, my original y, all the values of original y, I'm going to subtract it from the predicted y, and I'm going to square every term and add into the previous one. This would be my formula, and this is what we call sum of squared errors. Now, if you are not a beginner to machine learning, you must have learned about few errors: mean squared error, mean absolute error. So the word mean means add all the values. Let's say y1 plus y2 plus y3. What is the mean of these three values? You add them, divide by 3. So here you are adding all the errors for sum of absolute error. And if you divide it by the n value, number of values, you would get a mean value for the error. And this is what we call mean absolute error. And similarly, if I divide this error divided by n, I would get mean squared errors. That is a topic for another video. Right now, I'm gonna ignore them. But I'm telling you where those mean squared error and mean absolute errors are coming from. Right now, our focus is to minimize this error. That is our focus. So minimize this error. That is our focus. And how I would get those two values, m equals something and b equals something, remember, this is our end goal, right? We need to derive this equation and this equation. So how to get to there? We're going to use this function highlighted in black color. Okay. Now, why this is a good function? If I plot this particular function, let's take a look. So if I plot this particular function, I would get something like this. So if I plot this function, I should be getting something like this: a parabola, quadratic function. So this is a general x squared function, y is equals to x squared line. And this is the vertex. Ideally, yes, it is not centered, but let's assume this is the center. Okay, I'm drawing it by hand. So you can see it is a curve here, which means if I make a tangent at this particular point, let me change the color. If I make a tangent at this particular point, it would be horizontal. And remember, horizontal lines have zero slope. And slope is basically what we did over here. We wanted to figure out the slope in this vicinity. At this particular point, I cannot determine the slope. Why? Because in the neighborhood of it, on the left-hand side, the slope is negative. On the right-hand side, it is positive. And over here, it is undefined. If it is undefined, you cannot define it. That's why it was not differentiable. But at this particular point, if you zoom into this value, it would be very close to 0. And if you zoom into the right-hand side, it will be very close to 0. If both left-hand side and right-hand side are telling you the same story, the function is differentiable at that particular point, or in the neighborhood of that particular point. So we would say it is differentiable. So it is differentiable indeed here. And we want a differentiable function. Why differentiable? Because now we want to take derivatives. We want to find the slope. And if the function looks like this is what we call a convex function. Now, you must be asking, what is a convex function? Convex function is a function that if you start joining 2 points anywhere on the graph, So take a one point on the graph and take another point on the graph and join them with the line. If that line is always above this vertex, we call it a convex function. Always. And this is a convex function, no matter where you draw the line. So this point, this line is above this black graph. So if I take a line over here, so this point and this point, it is above it. Means you won't be able to make a line which is below it. And that is the definition of a convex function in simple terms. Excuse me. So this is a convex function. Convex function always have one minimum. One minimum means the minimum value of it, which means at this particular point, the slope needs to come to 0. So technically what you mean to say is the slope on this side at any point, if you make a tangent on the line, it is a negative slope. And over here, it is a positive slope. But at this point, it is 0. So it's technically you are reversing the car and then get to rest and then start moving forward. Without coming to rest, if you move forward, something wrong with that here. That does not make sense. In this graph, it does come to rest and then go the opposite direction, which means this particular function does come to rest somewhere in the middle, and that rest is what we are looking for, we are aiming for, and that is what we do in least square regression. So least square, that means this is a square function and I want to find the least value or the smallest value of it. And where it's going to happen, this x value is what I need to figure out where this would be 0. So this function is minimum here. If I have another function like this, it is 0 here. So what would be the x value at which I'm getting the lowest y? If I have a function like this over here, what would be the x value where I'm getting the lowest y? And if I have a function over here in this quadrant, which means what is the value of x here, which is giving me the lowest y value on this graph. So I hope that makes sense. Now, before we get to the next part, I need to explain you something. That how do we know? So over here, I just told you that this is the minimum. So it is a convex function and that's why it always have one minimum or something. But usually majority of the time, when you come across a particular problem, you will not have a convex function. Sometimes you will have your loss function, something like this. So like if I define it, your loss function would have some minimum value, some maximum value, and then it would have some saddle point, something like this. So this is your function, let's say. If this is your function, and I'm saying that wherever the slope is 0, that is where we have extreme values. So whenever we have a function like this, we will have extreme values. When I say extreme values, I'm talking about minimum value and I'm talking about the maximum value. So first of all, determine where the slopes are 0. So extreme values are the values where slope is 0 on the graph. 0 means how do we know slope? We make tangents on curves. So whenever the tangent is horizontal line, at this point, I can see it would be a horizontal line. At this particular point, I can see it is a horizontal line. It's kind of like a ping pong ball. It is bouncing off at this point. It is bouncing off at this point. This is line, this segment of the line from here to here looks like a horizontal line. At this particular point, it looks like a horizontal line, which means I have 1, 2, 3, 4. So I have 1, I have 2, I have 3, and I have 4 different horizontal lines on the same graph. And here you can see that if I touch 2 points, this point and this point, the line is above the graph. So here in this region, it is convex. But what about this point to this point? Here, the line is below the graph. Remember, I said the definition of convex function is if you join 2 points, those 2 points joining line would always be above the function, above the graph. Here it is not the case, which means it is not a convex function. If it is not a convex function, then it can have more than one extreme values, more than one minimums, more than one maximums. It is kind of like a valley going up and down and up and down. We don't know how many ups and downs are happening. So how do we know which one is a minimum value and which one is a maximum value? And the third thing we call a saddle point. First of all, let's understand the simple basic mathematics of it. First thing, you figured out the 4 points where the slope is going to be 0, which means if you make a tangent, that tangent slope 0 means horizontal tangent. Now, what is a tangent? I'm just saying it out loud. Tangent is a line which touches only one point on the curve. Any line which touches only one point on the curve, we call it a tangent. On a curve, it is usually just one line. At this point, this is the only possible line which touches this point, not more than that. So that's why we call it a tangent. Similarly, this line, similarly, this line, similarly, this line, and so on. Now look at this particular point. How do I know this point is a minimum or a maximum or a saddle point? This point the same way, this point the same way, this point the same way. So which means 1, 2, 3, 4 points. I need to determine which one is what. How do we do that? We go on the left-hand side of every point. So this is a point, go on the left-hand side and find the slope at any point. So at this point, I can see the slope is negative. And go on the right-hand side and find the slope at any point. I find the slope, I get a positive. So here, on the left-hand side of this point, the slope is negative. On the right is positive, which means the slope is changing from negative to positive. Over here, at this particular point, the slope is positive. How do I know positive? It is inclining up. And at this particular point, the slope is negative. So it is going from positive to negative. Over here, the slope at this point is negative. The slope at this point is negative. So it is going from negative and staying negative. At this point, the slope here is negative, going downward, and slope here is positive. So it is going from negative to positive. Now you see a trend. I can see this is the lowest point, this is a lower point, this is a top peak point, which means whenever the slope on the left is negative and slope on the right is positive, which means whenever you get a point around which the slope is going from negative to positive as you go from left to right, this is a minimum function, which means this is a minimum function, this is a minimum, not a function, minimum point, this is a minimum point, this is a minimum point. This one, when the slope goes from positive to negative, this is a maximum. And when the slope does not change, so here I used only example when it was negative, it stayed negative. It can also be true when it was positive, like it is doing something like this and then become like this and then doing like this, which means at this particular point it is this, but here it is positive, here it is positive, so it is remaining positive to positive around this particular point. So this one and this one is the example of saddle point. So this 3 is a saddle point. This one is also a saddle point. Now we have a good understanding, minimum, maximum, and saddle point. So technically here, this would be very handy when we would be doing gradient descent. And you will understand gradient descent better if you understand how to determine it is a minimum. Because what gradient descent is basically moves either left or right. And how does it figure out whether to move left or right? This is the background theory. Okay, I will cover that when I get to gradient descent. Based on that, I will cover that again. But for now, I wanted to do that because since I'm doing this from the scratch and I'm assuming there are some beginners, so I'm just doing that. So if it is a review for you, that's good. If not, then you just learned that. Now, moving on to next part. Our function, the error function, looks something like this. So I'm going to use this sum of squared errors. Let me highlight this. Let me give it a color. So I'm talking about this error. So this is what we need to minimize. If you look at this particular function, this function is a square function over here. How do I know this is a quadratic function? What is a quadratic function? This parabola function. How do I know that? Because it follows the general equation of the line. So let me pull this error and let me write it down here. So when I show you this error, it would look something like this. So let's write in black color. So sum, or maybe I would just use the short form, sum of squared errors. And that is equals to sum of all the values from I is equals to 1 till n. And the original values, all the values minus the predicted value, and then I square it. So this is my error. And if you look closely, this function is a function of yi. This predicted value is kind of like fixed, you can say. Means you have determined it. Okay, that's one way to say it. Or the other way to say it is basically not determined it, but what I would say is, uh, remember this predicted line is a straight line, and the equation of a straight line is mx plus b. If you don't know what this line means, watch the previous video where I covered the intuition behind linear regression. I discussed what this m and b are, so I'm not going to go in detail again. So the link is in the description. Please double check it. Do watch it if you don't know what that is. So which means this is the line for our predicted line. So I can replace this predicted line with mx plus b. So when I say x here, which means this x should get an I value when I substitute it here. So sum of all the values, I is equals to 1 till n. And I'm going to substitute yi minus. First, I'm going to put it in the bracket n. And this would be xi, because since I'm doing summation, that means for every x value, so y1, y2, y3, similarly, I have multiple x values as well, which means I need to figure out this predicted value for every x value. So this x needs to be substituted depending on which point I'm talking about. So mxi plus b. Because m and b are fixed, not changing for that line, so they should not get that I. And then I will close the bracket, square it. Now let's open the bracket. This negative is going to multiply here, distributive property, and this negative is going to multiply here. And we will get an equation like this. Y equals 1 till n. And I'm going to say yi minus mxi minus b whole squared. This is my sum of squared error, and I need to minimize it. When we do least square regression, what we do is, so remember how to minimize it. Minimize it means the slope, anywhere the slope is 0, that would be the minimum value on a convex function, which means this particular function, if you look closely, it would look like this, which means it will have, at this particular point, I can see it is bouncing back up, which means on the left hand side the slope is negative, on the right hand side it is positive, so it is a minimum, which means I need to find that x value, so this x value. How do I do that? This is where calculus comes into play. So what I'm going to do is I'm going to simplify a few things over here. So instead of calling it sum of squared errors, I would call it a loss function. Instead of loss, I would just call it L function. And I can see this loss function is dependent on m value and b value. Why? Because in the intuition part, we learned that by changing m, the overall answer over here is going to change. By changing b, the overall answer is going to change. So we need to figure out the ideal m value and ideal b value. That should give us the overall sum here equals 0. That is our goal. Now, which means I can write this function as, it is a loss function. It is dependent on m value and b value. So I would say it is a function of two different variables, m and b. And if I write it like this, I would get something like this. Over here, I'm also making something simplified because we would be deriving the equation. I don't want to spend a lot of time writing unnecessary things, even though these are not unnecessary, but you would understand it. This I value is always ranging from 1 till n, so I don't need to mention it. If I don't mention it, it is assumed it is going from 1 till n, and it is all the integer numbers. Then this yi minus mxi minus b whole square. So that's my loss function. And if I want to find the minimum of it, then I need to find the minimum, because m value is basically one of the value that I need to use to tweak it. So technically, if you understand, I have two knobs. One knob is the m and one knob is the b. And I need to adjust those knobs in such a way that this loss function ends up getting 0. That is our goal. Which means over here, I need to take the derivative with respect to, so this loss function, I would take the derivative with respect to m, and I will take the derivative of this loss function with respect to b. So this, if it is not a partial, if this loss function was dependent on one variable, I would have written as dl by dm, let's say it was dependent on m only. If that is the case, you write this d, but when you write the D is something like this, a crazy one, a mirrored 6 kind of a thing, this is telling you that the function is dependent on multiple variables. The first one, however many variables it depends on, you need to find the minimum of every of that loss function based on with respect to every variable it is dependent on. So I need to find the minimum loss value and what m value is going to give me that loss value. And I also need to find the loss value minimum and what b value is going to give me that value. For that purpose, now in the last video I told you that what does partial derivative means. Partial derivative means that when I'm taking derivative of this loss function with respect to m, I will assume everything else as constant. And if I take a derivative of this loss function with respect to b, I would assume every other variable as constant. And if you are not familiar with the derivatives of constants and something like that, let me quickly give you that if you have a function which is a constant, let's say a 5 number, so derivative with respect to x or y or whatever, it is always 0, which means derivative of a constant number is always 0. Derivative with respect to x. So if I have a function x and I'm taking derivative of x, it gives you simply answer 1. And if I have the power rule, say something like this, if I'm taking derivative something like this, x squared, let's say, what does this mean? First, I need to bring down this 2. Then I will write this function as it is, x, and then I need to subtract 1 from the power. And then I need to take the derivative with respect to x of whatever was under the power. This is also called the chain rule. Chain rule is basically that this power, first you take the derivative, first you apply the power rule. Power rule says that you bring down the power, write down whatever was under the power as it is, then subtract 1 from the power, and then take derivative of whatever was under the power. And you keep on doing that until you get rid of all the powers. Does that make sense? So what I mean to say is the chain rule would look something like this. I would take x squared and then I will take x squared. So first thing first, how should I do this equation? So in order to do this particular equation, what I would be doing is, first thing, I'm going to bring down this 2. Then I will write the whole function as it is, x plus x squared. Then I will subtract 1 from the power. And then I will take the derivative d by dx of whatever was under the bracket, under the power. So 2, so whatever was inside the bracket here. So x plus x squared. The next step would be, this 2 would be as it is. This x plus x squared would be as it is. And 2 minus 1 would end up giving you 1. I don't need to write it. And then when you take the derivative, so here, first you take the derivative of x. Derivative of x is 1. So I will get 1 plus. Then you take the derivative of this thing. And how do you take the derivative of this thing? You bring down this 2, write down whatever was under it as it is, and then subtract 1 from it. You would get 1, and you get this. This would be the answer of the derivative of this particular function. But for now, this would work, because here we are doing a square function, so you should be able to do that because I just gave you an example of a square function. So which means I need to find these 2 derivatives. So first I'm going to do an easy one, this one. So let's do the derivative of the loss function with respect to the b variable. If I do it with the b variable, so here when I take the derivative, this 2 is going to come down. Then I will have a summation sign. That I goes from 1 to n, I'm not writing it. Then you can see the bracket is going to be as it is, yi minus mxi minus b. Then I will subtract 1 from the power. And then I will do the derivative of whatever was inside the bracket. So I will do it like this. So I will do the derivative with respect to b of whatever was inside the bracket. So you see over here, I did a very, very, very similar example here. So now whatever was inside the bracket, I'm taking derivative of that. So I'm doing just that. Here, anyone who already knows this stuff, please skip forward these first few steps. I'm just doing it for the people who are struggling with the simple basic calculus. So I'm using analogy. So I used a simple example, and now I'm showing it over here. So now, first I will write this, and in the next step, I'm going to take the derivative. So I will write yi minus mxi minus b. Now this 2 is written as it is. This sum is written as it is. This bracket is written as it is. 2 minus 1 is 1. I don't need to write it. And now let's take the derivative. See, b is my variable of concern. Anything else is a constant. Yi doesn't have b in it. So derivative of a constant is 0. So you will get a 0 here for this term. Minus. This value doesn't have the b variable. So the derivative over here would be 0. This one has, so negative is this. So derivative of x with respect to x was 1. Derivative of b with respect to b would give you 1. So technically over here, you end up getting what? Negative 1. And this negative 1 can be multiplied and written outside over here. And we just figured out the loss function's derivative with respect to the b variable. Negative 2 summation yi minus mxi minus b. That is what we got. Now remember I said that I need to, so this is the slope where slope as compared to b, how the slope is changing. And remember, we need to figure out the minimum of it. And how do we find the minimum of it? This minimum is when the slope is 0. So this is the equation of the slope with respect to b for this loss function. I need to put it equals to 0. If I put it equals to 0, now I can solve this equation. So let me rewrite this equation, something like this. Negative 2. You can see this negative 2 can be divided on both sides, and this negative 2 is gone. I have this summation sign. Then I have this yi minus mxi minus b equals 0. So I get this equation. From here, what I'm going to do is I'm going to distribute this summation sign. So this is the sum of all the yi values minus sum of all the mxi values minus sum of all the b values equals 0. Now, if you think about it, we wanted to get an equation of b equals something like this. This was the y mean, or the mean value of all the y's. This was the mean value of all the x's. That means this summation sign that we are getting over here. Remember, what is a mean function? Mean function is you add y1 plus y2 plus y3 plus y4. How many values I added? 4 divided by 4. Another way to write it is something like this. Summation from I is equals to 1 till 4 on yi divided by 4. Another way to write it, you can see this summation sign is there. That means this numerator is there, which means here my I values are going from 1 to n. That means if I divide every number by n, what I would get, this would give me the mean value of the y. So mean value of the y, how am I labeling it? This y bar. So this y bar tells you the mean of it. Minus m is a constant here, so I would write m. Summation of xi, which is all the sum of x's divided by n. That means this is the mean value of x, and this would be the mean value of b here. Remember, we wanted to figure out an equation for b. This is a negative here. That means if I add b on both sides, I would end up getting b equals y mean minus m times x means. And this is the equation we were looking for. And I just figured out that equation. So we just figured out one equation already. So this equation is what I wrote over here. That means now I know what this equation means. Now you can find the mean of b very easily. So you have the data points, right? So I will go to my data point. So this is my data point table. So how would I find the mean value of y here? Add all of these values up divided by number of values. So 40. So it would be 40 plus 50 plus 60 plus 85 plus 80 plus 75. How many values did I add? I added 1, 2, 3, 4, 5, 6. So divided by 6. So we got an 65 value. So this is my y mean. Now, the other part of the equation is x mean. Can I find the mean of the x values? I can also find the mean of the x values, which is this plus this plus this plus this plus this plus this divided by 6. Let's do it. 4 plus 6 plus 5 plus 10 plus 8 plus 11. Divide by 6. You get 7.33. So x bar is 7.33. So if I want to calculate the value of b, I need the mean value of y, which I got from this x and y variables. I got the mean value of x, which I got here. I need to figure out this m, and this m value is what we can get from here. So far in this b equation, I can find this y bar, I can find this x bar. I need to know this m. If I can know this m, I need to just substitute 3 numbers here, and I have the perfect b value here. So let's find this m value now. So what I'm going to do is I'm going to go back and I'm going to do the derivative of my function. So here I did the derivative with respect to b here, right? I'm going to do the same thing with respect to m now. And I'm going to find the minimum of it. Let's do it in a different color. So I need to find the derivative of the loss function, or partial derivative of loss function with respect to the m. What was my original loss function? My original loss function was this. So I'm going to copy this over here and I'm going to write it. So I need to find the derivative with respect to m of this loss function. It was sum yi minus mxi minus b whole square. Now let's apply the derivative. Here I'm going to do some quick steps because I hope that you understand how we did in the previous one. So first I'm going to bring down this 2. Then the summation sign would be as it is. Then I will write this bracket as it is. Yi minus mxi minus b. And then I will subtract 1 from the power. 2 minus 1 is 1. Then I will take the derivative of this bracket. So derivative of yi, this yi doesn't have m. Now my m is the variable of concern. So this one doesn't have any y. So derivative of a constant would be 0. Minus. This is m and xi is a constant. It's kind of like when you have 2x and when you take the derivative with respect to x of 2x. Remember, derivative of x is 1. 1 times 2 is 2. So this 2 can be pulled out before you take the derivative of x. Similarly, this m is the constant variable here. X is the constant. Xi can be pulled out. Derivative of m is 1. 1 times xi is xi. And this negative sign remains as it is. Then minus b. Now keep one thing in mind. This b variable we just determined here, it does have m inside it, which means it is not a constant anymore. Which means I need to go back here and I need to replace this b over here. So this would be y bar minus mx bar, and that should be my function. And if I open the bracket here, you can see this negative y bar. And the y bar doesn't have m value in it, so derivative of this one would be 0. This negative is going to make it positive. And then the derivative of this mx bar is going to be x bar. And that is what we are going to end up with. So let's simplify. So this is 2 summation yi minus mxi. Now here, I substituted the b value here, but I need to expand this as well. So this would be minus y bar plus, so because minus would make it plus mx bar multiplied by negative xi plus x bar. We get this. Now, think of what exactly I need here. I need something like this. So xi minus x bar, xi minus x bar, yi minus y bar. Xi minus x bar somehow, which means over here, I need to do something so that I get that kind of an expression. Before I get that, keep one thing in mind. I need to minimize it. If I need to minimize it, I need to put this whole thing equals to 0. If I need, why? Because we know that when the slope is 0, that is where the minimum of the function is. So we are figuring out to be 0. This 2 can be cross multiplied. We got rid of this 2. I can pull out this negative here. Why? You would see why. It is mathematically convenient for us. So I would pull out negative 2. So this negative is here. So 2 is already here. So I pulled out negative. So I can write negative 2. Summation yi. And here what I'm doing is I'm writing the y terms together, yi minus y bar. And I'm writing the x's terms together. So minus mxi plus mx bar. And then I can write, since I pulled out this negative, I will get xi and I will minus x bar. Now this negative 2 can be divided on both sides and become 0. So you will get 0 equals sum. Now what I can do is I can open this sum. So this summation sign can be written with yi minus y bar. And this xi minus x bar, you can see there is a bracket, which means this xi minus x bar, this whole bracket is multiplied with every term. If I kept these two terms together, which means this xi minus x bar is going to get multiplied with this. And this summation sign will continue here. So I will pull out negative summation. And then since I pulled out negative, I will get mxi. Since I pulled out negative, this will become negative mx bar. And this xi minus x bar is getting multiplied with this section of the graph as well. So I will do xi minus x bar. Here you can see xi, x bar, something is common. M is common. I can pull out that M. Here, yi, something like this. So if you look closely over here, my equation would turn out to be, so this is a negative, which means this whole term, I can move it on the other end and I will get this whole term equals to this term. Then I will get a 0. So I will write sum. This M is being pulled out, so I will write outside. And then I'm left with xi minus x bar times xi minus x bar. You can see this is the same term, so why not just write it as a square? Equals. Then I'm left with summation yi minus y bar times xi minus x bar. I wanted an equation for M, right? So I can cross multiply this part on the other end and I will get something like this. So summation of yi minus y bar xi minus x bar divided by summation xi minus x bar whole square. And this is the equation we were looking for from the start. We just derived this equation from the scratch. Yes, it is a pretty long video, but you can see this is the equation we were looking for. Here, this M value is totally dependent on Y values, the mean of the Y values, X values, and the mean of the X values, which means we can get the M value from here, substitute it back here. We can find both M and B with a direct formula without knowing anything, which means if I just give you the data, you don't need to do iterations. Now you have a direct formula to get the value of M and get the value of P. Okay, so let me write down the B value here. So B value is Y bar minus MX bar. Thank you so much. I will see you in the next video where we will implement using code in Python, using NumPy from the scratch, our own simple linear regression class. And we're going to compare it with sklearn's built-in linear regression class. And we're going to see our class and that class gives you exact same results. So I will see you in the next video. Have a good one.